Based on conservation of energy principle, there is a problem that relates to work and energy. The problem statement is given here. It is suggested that you can pause the clip and read the statement carefully. I am simply going to explain what the problem is using this diagram. There is block M2 and there is a block M1. They are attached through this string and the pulley arrangement. Initially the system is at rest because it is held in that position. This block M1 has tendency to move down. And how do I know that? You have to read the problem statement, that it says the system is released from rest position when blocks M2 is pulled horizontally. So this block moves in this direction because of the weight of block that has the mass M1. That means this block. And it is observed that mass M1 gains speed of v, which is given here, on descending vertically through height h. So when this, let me take this mark which not needed, you already know that that is M1. Okay, it's not coming off, that's fine. So this block moves vertical distance, which is h, and its velocity is v at the end of descent of h. Now there are a couple of things. Before that, what is asked? What we are asked to find is we have to show that the coefficient of friction mu is given by this relationship where we have M1, M2 in that ratio. The velocity v is appearing here, and g is of course the gravitational acceleration. We will do this problem, but before that we need to analyze how to bring and use the principle of conservation of energy. First thing, the block M1 is at rest, so its initial kinetic energy is 0. As soon as you release the system, because of the weight, the block M1 starts moving down. So it has only potential energy to start with. If you recall, potential energy is due to height or configuration. So the configuration is such it's held in position. If you release it, it starts moving. And so the potential energy gets converted into two forms. One is that it works against friction in moving this block in this direction, that's the block M2, and also the remaining energy is left with block M1 because it still has velocity v. So very important thing to observe is that the initial potential energy must be mgh, which is equal to work done against friction in moving M2 through distance, and I'm not knowing this distance, so I'm simply saying through distance d plus the balance of kinetic energy, which is 1/2 mv square. Now this distance d is the key to the factor to the problem solution, and so we'll see how the distance can be found. If I call this point as A, this point as B, this point in line with this string as C, and this point as, say, D, I notice certain thing from these lengths, that DC is constant. It's not going to change. Whatever happens to the position of this mass M1, the length DC is always constant. When M2 moves, what changes is A, B, C. This length is changing. This is variable. Now, from the data which is given that distance moved is h, you can certainly know that this point, and I'm putting this on the table at this location, if this point on the string moves distance 2h, that means this point comes here, and this is x, and this is x prime. This 2h is going to get accommodated in ABC, which is this variable. So if this is 2h, then only this M1 can move through distance h. And this is important observation. So if the mass M1 descends through distance h plus 1, the horizontal movement of the block will be h plus 1 times 2. It will be exactly 2 times whatever is the distance the block M1 descends. And so we write that this d is nothing but 2h. This is equal to, now all we need to do is find the work done, which is force times distance. Now distance is already known, which is 2h. What is the force? Force of friction, normal reaction to the mass. I should mention that this mass is given as M2 and this is M1. So M2 is the mass, so M2 times G is the weight, and the same is going to be the normal reaction. Friction is obtained by mu n, which is mu times M2 times G. So this is going to be the work done against friction plus 1/2 M1 V square. Again, here mgh will be actually M1 gh because the mass involved is already given as M1. So now let's solve this for mu. So this is equal to M1 gh. By transposing this term, we have 1/2 M1 V square 2 mu M2 gh. This implies whenever there is equation, the subsequent steps are always implied by that equation. So we write implies mu is equal to m1 gh minus 1/2 v square. I'm solving for this mu, so I have, and I'm going to write this mu times 2m2 gh, so that I can bring whole this thing underneath so that it divides it, m2 gh. So now the further simplification can be done, and so we have mu equals, and so we can write 1/2 m1 over m2, and this gh in the denominator can be sent in the parenthesis, so gh over gh is 1 minus v square over 2gh, and then this is what is asked actually, and that's the answer. So anytime you have these two masses given, m1 m2, the velocity given and the vertical descent is given, you can find the coefficient of friction.